Good afternoon, my name is Daniel Hennigan, and this is my first capstone project for EET 490. It's a test set for MC130J communication cord. It's a communication cord for on aircraft. So that's me right there with the test set powered up, showing that it is portable. So it can run off a 9-volt battery that's inside of it, as well as has an AC to DC converter, so you can plug it into the wall, or it'll run off of a computer with the Arduino program. So this is what it will be testing. It's the communication cord that aircrew and maintenance use, and we'll go over exactly what it's doing in the video. However, as we can see, this cord, there's a lot of parts to it. A lot of parts can fail on it, so my tester will help technicians troubleshoot and hopefully repair and turn these into serviceable. So these are the materials that I used. Arduino Mega first and foremost, and then I have the 8 LEDs for the different pins in the wire harness itself, because in that last picture there are actually different pins in the wire harness. I used a 12 or step-down transformer getting to 12 volts AC. Then I went through a full bridge rectifier, a few capacitors to help smooth that out. I had these different values of resistors and the LCD screen, so you could display messages. I have a 10K resistor on each of the pins to help calculate current, which we'll go over as well in the video. Then I have these two resistors and for the voltage regulator to help me to get to about 11 volts DC. I have a fuse, connecting wires, and the aluminum box. All right. So here's just an overall schematic of what the main test will be doing. So we have a couple push buttons, and these will register a fail or a pass, sensing when it goes to ground, and we're holding on while loops. We have the screen, which the LCD screen. Then we have the cord under test, which goes through the 10K, and we're also sensing at two different areas. And as we can see, we're reiterating this through each pin, so there's a lot of wires in a lot of areas. When we open up the box, you'll see. So here's our quick little AC to DC converter. It's a step down going to a switch, a safety switch down here, and the fuse, a couple capacitors, and we have this formula right here. And on top I have R2 is 8K, so it's 8K over the 1K plus 1, so it gets us to about 11.5. But in reality it's about 11.3. But we'll see that too. So here's some pictures of me building the tester, so soldering on to my bank of LEDs for each pin, and this last LED is for the ground wire, or if it's good, test set good. A small AC to DC converter, so this is the massive transformer. You can see the fuse goes down here, a few capacitors, and the switch. And then here's the LCD screen, the 1602. And as I mentioned before in my proposal, these are the weak areas that you have to be very careful about with these cables. And also the test set will let the technicians know that these are the weak areas, and that's where the majority of the faults do lie. However, there could be faults in the cable at other areas. All right, so let's watch the video.
Good afternoon, my name is Daniel Hennigan, and this is my first capstone project for EET 490. My project is titled MC130J Communication Cord Tester. All right, let's begin. So this is my project for EET 490, the MC130J COM cord tester. This is the cord right here, unplugged. So this is what the aircrew would connect to the aircraft and plug in their headsets here. And this is a push to talk, which we'll have to test later. So there's about 8 individual wires. There are 8 individual wires in this cable harness that we'll be testing. And what happens is, since the aircrew and maintenance personnel always use these cords to communicate on and throughout the aircraft, individual wires go through a lot of stress. They get frayed, semi-broken, shorted together. So the technicians have a little bit of trouble finding out which wire it is, which my tester will help them with, and also teach them about the cable. And my test allows a hold on each pin, because some of these cords, there's other variations of it, and some of them are up to 300 feet long, and the technician has to go in and manipulate and flex test the cable harness as they're testing it, because sometimes there's a pinch and the wires are broken, but they're still making contact at that point when they're testing, so they really need to flex it, which they'll see real-time resistance reading of the cable harness. So the overall theory of my tester is that I have an Arduino in there that's reading it, so I'm sensing the voltage here coming in here. So right here I'm testing the voltage, so I know the voltage drop across my cable harness, which is represented here. So my voltage drop across the cable harness, and I'm taking another voltage reading across a 10K resistor and the constant voltage drop of the diode. So that means I have the voltage here and across here. That means I have my voltage drop across my cable harness for that pin. Then what I do is I know that this LED is a constant, so I have the constant minus the voltage drop to get the resistor's voltage. Then I take the voltage and the resistance to get the current of the line. And finally, I know the voltage, I know the current, so I could get the real-time resistance reading of the wire itself. And it'll also, if any of these are shorted together in here, it'll turn on another LED. So that's my test set, schematic. And also, on the back, I wanted to install an AC receptacle. So there's a transformer in here, which goes through a full bridge rectifier, through some caps, and I had a variable inline voltage regulator, so I have about 11 volts powering the Arduino. And then I also have a battery switch, so you could go from powering it through the AC, powering it through a standalone battery, or a standalone computer with the Arduino system, which what we'll be using throughout our test set so we can see the output screen. But to show that the battery works, go here, and there it is. It's running the preloaded test, telling you the quick instructions. So if we turn the battery off, that one, and we have our, oops, let me put this up real quick. Plugging in our AC. You can see our AC is now plugged in, and it goes through this switch down here for safety. So if we turn that off, the AC is now off. Okay, but for our project, we'll be using, our demonstration, we'll be using the tester, or the computer. All right, and the first thing we'll do is we'll set up and plug these in. That's the overall. Sure, here we go. Welcome to the tester. Instructions, test, connect it, which we just did. A little brief instructions. Usual decide using the above buttons. Until a button is pressed. All right, would you like to print screen? So if we say yes, we go to serial monitor. Ooh, might have to, should have had that up first. So we'll have to redo that because we didn't have that guy. Here we go, capstone 2. And then we'll see our serial monitor. And we go through my code to be provided. So there we go, general information, some part numbers, and it's starting to begin our test. So this general information supplies everything you need, the technician would need to order a part. These aren't the actual part numbers, just a caveat, because I didn't want to print to YouTube what the Air Force part numbers use, but I'll change those, and the TL publication as well. And just some brief, what the tester is, who developed it, some general information. All right, so right now, it's testing the first pin, and there's a little fluctuation in the resistance reading, but overall it looks pretty good. We have our one LED lit and no others are lit. So we could go and say, yeah, that looks pretty good. Now for this pin 2, there's a switch in the back you'll need to swap over to make sure it is working. This one. So, yep, in the correct position. However, if it was not in the correct position, there we go, and it would say open. That's because some of the pins share the same line. So there we go. And we'll make all the pins pass for the first iteration of the test. Ooh, there we go, it passed. And we're gonna have to flip this switch back over. Switch one position, okay. Letting given time for the technician to know. So see, it's gonna say that, but it's gonna say open. It's because we need to go here. And it's still saying open, but we need to press our switch, blue for, here we go. A little high, and then it drops down. First initial reading is always a little high. Yeah, it looks pretty good. Turn it off, turn it on. Okay, so it takes a little time for the system to catch up to it, but there we go. Good reading. All right, so we'll say that one passed too. And then it's gonna replicate through the rest of the pins. There we go. Pin 5 passed. Pin 6, a little high, and it's gonna drop. So we'll say that one passed. This is a known good cable, by the way. I also ship with it. And then the instructions, if they suspect that test set is bad, then they could use the known good cable to verify that the test set is good. We're running through the rest of the pins, and it tells you what the wire is called in the schematics. So yeah, passed. There we go. And let's see what happens. So COM cord passed all tests. Return cord to service. So that means back on the aircraft. So it's in service. Filled pins none, and it's green. Okay. So would you like to retest? And this time, yes, let's retest and see what happens when we fail a pin. So that one looks good. So let's say, yeah, number 1 is good. And what I have done, I've mocked up a little potentiometer. Let's make sure it's on the correct pin first. On the back switch. Here we go. So I mocked up this tied to a potentiometer to show the real-time resistance reading if there was actual fault. Oops, tape fell off. I'm going to clamp it to where it goes. And if we see here, okay, so it's open now, and as we move the potentiometer, it's about a 10K pot, so I'm turning it down. There we go, down to 5. So it's the real-time reading of the line just to show proof that I'm actually reading the resistance of a 10K pot. All right. So let's say this one failed. And it's telling you to go back, switch it for the blue button. Let's say this one failed too. Let's say this one looks good. We'll pass it. Just a random selection. Let's see what will happen. I also wanted to do this because I didn't want it automatic because maybe the technician wants to inspect while they're running the test. So they take it out, look at it, and it'll say open, but it won't automatically fail your test. So let's say this one, let's say no, pin 8 failed. Oh, and I forgot to almost show you that as each pin is selected fail, it gives a reading of what that pin is. So pin 2, every time we click that button, and then it shows you where pin 2 is. Pin 2 is headset low and connected to the black wire on the rightmost contact of the female connector. So it gives a brief description of everything that's going on. Every time you click a pin fail, it prints it out if you have this connected. But like I said, you don't need it. Let's say this one passed, and then we'll see what happens. So it says failed pins, and it tells you what pins failed. And you can stay here. Test it. So would you like to retest? And say no. Thank you for testing. Please power off test set. So that's the end of the test itself, and let's go ahead and open it up to see what it looks like inside. It's a little tricky to get it off. Okay. We're going to disconnect power. So we're going to look inside. We're going to see this AC receptacle. Goes to this massive step-down transformer. The battery is in there. This is the switch to cycle through battery power, AC power. This is switched between the two buttons. So here are all our LEDs. They're all grounded at the same point except for this guy right here, which is needed because these two are actually tied together. And so you need this to be isolated with a switch. This is my LCD screen. And then I'm using a bunch of sense pins at the top of the cable harness and then also on this bank of resistors. So it comes through, goes to the resistors, if you could see them. There's some resistors down there, 10Ks, and then to the diode and then to ground, but the sense is reading also right there. There's two sets of wires. And then here is my adjustable voltage regulator being set to 11 volts because of these resistors, and a few caps to smooth that signal out. Also a fuse just for safety precautions, and then this switch right here. And so if we plug in this, which I don't recommend doing while the test set's open, that power on with the AC just to show it. Put them here. Sorry. So right now I'm just connecting up so it's running off of AC, and if we look at right there, it's about 10 volts per division, and it's right almost at 12, a little under 12 volts, which is 11.3 is what I read on the voltmeter, and that's showing this working right here, which is going from this rail, is jumping over and is soldered down to the switch. So everything is soldered mostly, except the things on the breadboard, but these are all soldered. And yeah, that's pretty much my test set to help the technicians troubleshoot. And like I said, I also printed out a hardboard set of instructions to help the user if they have any problems with it. The only thing that I have left to do is to put some screws in so the technicians won't be able to open this up. But I wanted to leave it open so everyone can see it and show you the smooth DC line shown on the oscilloscope, thanks to the capacitors. And if there are any further questions.
Alright, so that's my project for my first capstone. The reason why there's a little bit of a variation in that resistance reading is because I think when you calculate the current, it goes down into fractionary binary numbers. So what I did is I actually took an average reading. So I did a for loop and took an average reading of about 1,000 readings, and what you're seeing is the average of all those 1,000 readings. So that's why there's a little delay in the resistance reading. Alright. So if there are any questions, feel free to contact me over Blackboard. And thank you very much. Have a great day.